So in the previous lesson, we learned about conceptually the idea of regression. In this lesson, the least squares regression, we're going to talk about how to actually calculate that regression line and find it. So first, here's the roadmap. We're going to talk about what it means to best fit the data. What does it mean for a line to best fit the data? And then we're going to talk about sum of squared errors and why that concept is important for regression. Then we're going to talk about some quantitative properties of the regression line. We know conceptually what it means, but once we do have a regression line, there are some rules that the regression line conforms to. Then we're going to talk about how to actually find the slope and the intercept of the regression line. All right, so what does it mean to best fit the data? Well, you could think about it like this. There are any number of lines that you could draw through a set of data. So we could draw that one, we could draw this one, we could draw this one, we could draw that one, right? So there are an infinite number of possible lines. But our goal is a regression line that is sort of in the middle of all of these data points. And when it's in the middle, that's what we mean by best fitting line. So you could think of best fit as roughly being equal to the concept of in the middle. Okay? And so the difference between all of these lines and the true regression line is that the best fitting line is roughly in the middle. All right, so how do we find this best fitting line? Well, quantitatively, what it means to best fit the line means that this line has the lowest sum of squared errors. And because of that, the regression line is also called the least squares line, and that's why this is called the least squares method. So even though in the middle and best fit are good conceptual ideas, they aren't quantitative ideas. And so this is a quantitative definition of what the best fitting line is. Now, let's talk about what error is. Remember, we had a particular word for error, and that word is the residual. And that residual is the difference between y and the predicted y from our best fitting line. Having the lowest sum of squared errors is having the lowest, so SSE is really having the sum of all the squared residuals. So residuals squared, right? And another way to write that is by substituting in for residual, y minus y hat squared. So this is really our quantitative measure of how good our line is. Now, there's somewhat of a catch-22 here. We have to have the line before we could figure out whether it has the lowest sum of squared errors. But the question is, how do we find that line? But first, before we go on, let's talk about why we need to square these residuals. Remember we talked about what it means to be in the middle? It means that the distances on the positive side, or the points above the line, and the points below the line, the negative distances, these should all balance out. And so if you have a bunch of positive and a bunch of negative and you add them together, you should get 0, right? So here's the tricky part. The sum of the residuals, period, y minus y hat, so the sum of the residuals, period, that should be roughly equal to 0, right, for the best fitting line. Because of that, we want to square these distances. And I will write the squared in red, because that means that this value, the sum of squared errors, should be greater than 0. Right? And so because of that, we definitely want to square it. Squaring it also gives us other mathematical properties that we'll be able to take use of in the future. All right. So we know what it means to quantitatively be the regression line. It means having the lowest sum of squared errors. But there are some other quantitative properties that come along. One important property to know is that this line, the regression line, also contains the point of averages. So the average of all your x's and the average of all your y's, the average of variable 1 and the average of variable 2. This point is often also called the center of mass. And it's really easy to find this point. You just take the average of your x's and take the average of your y's, right? And so x bar comma y bar is your point of averages. You could also think of it as the center of mass, because if you think of all your points, the scatter plot, as almost like an object, right? This is the center of that mass. We already know that this line has the lowest SSE of any other line that also contains this point of averages. The sum of the residuals, right, when you don't square it, that should be approximately 0, very, very close to 0. And because the sum of the residuals is 0, the mean of the residuals is also 0, right, because the mean is the sum divided by the number of points. If the sum is 0, the mean is going to be 0, right? And the variation of the residuals is as small as possible. So it's smaller than other lines. One way to quantify variation is something like standard deviation, right? So the residuals have the smallest standard deviation than any other lines. All right, so those are 4 very important quantitative properties that we need to know. So this sounds like a wonderful magical line. How do we find such a line? Well, you might be thinking, well, this is sounding pretty hard. Maybe we have to find the sum of squared errors for a whole bunch of different line equations and find the one with the lowest SSE. Well, that's actually problematic. I mean, it's a good idea. It's a good conceptual idea, but it's problematic, and here's why. There are an infinite number of lines, right? Like every little line, every tiny little line. You could just change the y-intercept by 0.0001 and you have a totally different line, right? You could change the slope by a tiny, tiny amount and you have a totally different line, right? So there is an infinite number of lines that we would have to test, right? So infinite number of potential lines. We can't find the SSEs of an infinite number of lines, right? This is just not an option for us. So, thank you to our hero, Karl Gauss. He was a mathematician and all kinds of science guy, German guy, and he's helped us out a lot in statistics. Karl Gauss invented this method called the method of least squares. And through Karl Gauss's method, we could easily find the slope. And here's how we do it. The slope is going to be a ratio. I mean, slopes are always ratios, right? Rise over run, the ratio of change of y over change of x. And Karl Gauss's methodology sort of has a similar vibe to it. So here's how Karl Gauss finds slope. So remember, slope is not b sub 0, that's intercept, it's b sub 1. So b sub 1. And in Karl Gauss's method, you want to add up, so take the sum of all your x deviations, so the deviations between x and the mean, right? So x minus x bar, right? So all the deviations of x, and multiply that to all the deviations of y. Notice that we're not using x hat or y hat because we don't have the line yet, right? But we do have the center of mass, right? And we're using that. We're finding the deviations from sort of the center of mass, right? And that sum over the sum of x minus x bar squared, right? So it's sort of, think about this as the 2D variation over the x variation squared, right? And so when you think of rise over run, you think of the y over the x, or change of y over change of x. And so you could sort of see that here. There's the change of y, and there's the change of x. But here there's two changes of x, and here there's a change of x and a change of y, right? But this method will give you the the slope that is the slope of your regression line. Ta-da! And just as a review, remember that when we have this x here, we really mean x sub I. And when we have this y here, we really mean y sub I. And I goes from 1 all the way up to n, however many data points we have in our sample. But this often goes without saying, that we want you to do this for every single data point that you have, right? Don't skip any. All right, so that's Karl Gauss's method. All right, so in order to find slope, we need to use that function. So it's the change of x, the deviations of x multiplied by the deviations of y, all added up, over the deviations of x squared, right? The sum of the deviations of x squared. Now, let's actually do a little example here. So if we had a whole bunch of x's and a whole bunch of y's, I'll just put a few here. So x equals 1, 1. So the first point is 1, 1. The second point is 0, 0. And the third point is negative 1, negative 1, right? So it's a really easy line. We already know that the line equation should be something like y equals x, right? We already know that. But let's see if we could use Karl Gauss's method in order to find slope. And I often find it useful to tell myself, okay, I know this is where we're going. So the deviations of x and the deviations of y. So the sum of the deviations of x times the deviations of y, and the ratio of that sum to the deviations of x squared, right? Well, this means we're going to have to find x bar and y bar, right? And easily we could tell here, if we take the x bar, we just add it up. Adding it up is 0, so the average is 0. Adding this up, 0, right? So we already know x bar and y bar. It's a really easy one. Now, in order to do this, I'm going to have to find x minus x bar. Oh, let me draw this in a different color to make it easier on us. So x minus x bar and y minus y bar, right? Not only that, but I'm going to need to know I'm going to need to know x minus x bar times y minus y bar. And I'm going to need to know x minus x bar squared, right? So let me draw some lines here. All right, so let's get started. Because my x bar and y bar are 0 and 0, this makes life easy for me, right? And now let's find this difference, the x deviation times y deviation. So I would just multiply across. So that's 1, multiply across, 0, multiply across, 1, right? And then x minus x bar squared, so this value squared. So that's 1, 0, and 1, right? And then I need to find the sum here and take that and put it over this sum, right? And so this sum is 2, this sum is 2. So if I put it all in here, my B1 equals 2 over 2, which is 1. right? And so we've found our slope. Our slope is just 1, right? And since we already knew that the slope of the regression line here should be y equals x, we know that we're correct. Y equals 1 times x, which is y equals x. All right, so now we know how to find slope. But how do we find intercept? Well, once we have our slope, right? Once we have our slope, so let's use our previous example, b1 equals 1, right? And we know one of the points that falls on our regression line already, right? We know x bar comma y bar, right? Which is 0, 0, right? And if we know both of those things, we could actually find our intercept just by plugging it in, algebra style, right? And so our equation for the line in statistics is y equals b naught plus b sub 1 times x, right? And all we have to do is plug in our numbers and substitute in order to find this one. That's the one we're looking for. So if y equal, here's an example y, b sub 0 plus 1 times 0, right? And so here I get b equals 0, right? And so this step is really quite easy. This is just finding a missing value just by having an example y, example x, and having the slope, right? We could actually derive the formula so that in the future we'll know exactly what to plug in. So instead of trying to solve for y, we could just, just flip around some of these things in order to, so that we could solve for b sub 0, right? And so all we have to do is really move this over to that side. So that's y minus b sub 1 times x, right? And that's really how you find b sub 0, or the y-intercept.